Hey, what's up, guys? This is Chung here again. So, LeetCode number 1994, the number of good subsets. Okay, so this one is another like subsets or subsequences problem, right? So this time you're given like an integer array nums. We call subset nums of good if its product can be represented as a product for one or more distinct prime numbers, right? So for example, we have this 1, 2, 3, 4. These three are good subsets because the product can be represented as 2 times 3, this one, but this one is not because 4 itself is not like a good candidate because this one can be basically this one is like it's not distinct prime numbers, right? It's like a duplicated one. Same thing for what? For 9, right? 9 is also a not good one because 9 equals to 3 times 3, right? And then 16 is another one, right? 4 times 4, and then 25 is another one, right? Equals to 525. So something like this. So these numbers are by itself are not a good candidates, which means we cannot pick those numbers regardless, right? So that's one thing. And then return the number of this, blah blah blah, right? And then so and again, right? This one is a DP problem, right? But this one, so how do we get started? Basically, we have solved some of other like subsequences or subsets problems. If everything, basically if there's no constraint, right? The total number of subset or subsequences is going to be 2 to the power of n, right? So this one including the empty subset. So for this one, I think, yeah, I think it does not allow empty. That's why we have to do a 2 minus 1 in the end. Okay, but we can deal with this one later. So the the uh, the base of a subset is that if there's no constraint at all, right? So every time, I think I have already talked about this several times. We have this one, right? Let's say we have A and B, right? A, B. So the subset for this one is going to be A, B, A, B, and the empty string, right? So every time when we add a new one, right, it's going to be a AC, AB, A, B, C, and C, right? Basically, the total number of subsets will be doubled, right? But this one is like either constrained, unique, or like a good subset. I call this kind of problem. I think we can call it a constrained subset, right? Basically, you cannot blindly get whatever you want. You have to delete something, right, from it, or not add current number. So for this one, the constraint is like we want all the numbers we pick in the subsets has a unique distinct prime numbers. Can be the product, can be that, right? And how can we do it, right? um, so first, right, let's say we have the prime numbers are what the prime numbers are like 2, 3, 5, 7, 11, 13, right? So on and so forth, right? So let's say for number, let's say we already pick a number, right? The current number has already used the prime number, this one, and this one, right? So let's say for all the previous number we have already picked, those numbers have already used these three prime numbers, and then when we try to pick up the current number, right? We need to know the current number does not have any of this previously have already used prime number in it, right? So let's say if the current number is what, it's 10, then definitely this is not a candidate, right? Because 10, we have 2 and 5, right? So if we add 10 to the current subset, since we already used 2 and 5, then we'll have like 2 times 2 and 5 times 5, right? But I think 21 is fine, but 21 is fine, right? Because 21 is a prime like for 3 times 7, right? So we can use this number because by using these numbers, we have 3 and 7 later on, right? Which does not result to a duplicated prime number. Okay. So now, so basically this DP is like a knapsack DP problem. So basically, with the current numbers, we have two options. We either pick this one or we don't pick it, right? Based on what are the prime numbers we have used and what are the prime numbers these new numbers we're trying to pick will be added, are going to add to the prime numbers set, right? Cool. So in that case, let's go back to the problem here, the constraints, right? So the constraints is like the number is pretty long, 10 to the power of 5, but see, the number itself is pretty small, only within 30, right? Cool. So in that case, we can just start from this one. And regarding this kind of all the numbers, we can do a frequency. We can do a count for all the numbers. Okay, because let's say if we have 5 2, if we have 5 2 here, we can simply in the end, right? So no matter okay, so let's say by adding this 2 into the we'll have like 10 more subsets, right? And since we have 5 2s, right, we can simply do a 10 times 5 equals 50, which means that for all 5 2s, we will have like in total we'll have like 50 new subsets, right? This is because let's say we have different numbers, okay, and we have 2, we have another 2, right? Another 2, another 2, okay. Since it's all subset, right? We don't have to. We can pick any 2 from these numbers because it says the 2 subsets are different if the chosen indices to delete are different. Basically, if we pick this 2, it's different as we pick this 2. This 2 is this 2 are they are totally different, but by picking any of them, we're adding like the same base count here as 10, so that we don't have to worry about this long array. All we need is to like do the frequency, right, of each numbers, and then we just multiply the frequency in the end. Right, so that's another trick, right? And then okay, so now how do we check, right? How do we check if we can pick the current number, right? So remember we were trying to say if we want to know if the current number does not have any prime factors that has already been used before, right? So which means for each of the number, right, we need to get its prime factors, right? And then we need to do like cross comparison with the previous one. And what we can do is that we can use a bit mask, right? So since the number it's pretty small, right? Only within 30, right? We can have like a bit mask to tell us the what are the prime numbers we have already used, right? So let's say this one corresponding to 2, 3, 5, 7, 11, 13. Next one is 17, I guess, right? And then 19. Yeah. So whenever this one is a 1, it means that okay, so we have already used this prime number has already been used, right? So let's say for example this 2 has been used, which means we cannot use those 2 numbers again, right? And then that's the current mask. And then for the current number, right, we need to basically also make a new mask for the current number to tell us like what are the prime numbers that this new number will contribute, right? So for example, this number will contribute to this 2, right? It's going to be this 2 0, right? And how do we check if this two does not have any intersect? We simply do an AND, bitwise AND. If the bitwise AND equals to 0, it means that, okay, there's no intersection, right? If it's 1, if it's not equal to 0, then it means that, for example, if this one also has like this as a 1, right? Then the final AND, bitwise AND will not be equal to 0, right? So that's how we can quickly check, right? So that we don't have to like do a cross for loop here. We can just use one O of one time to check if this one can be added or not. Okay, and that's that. So, and there is one last thing we need to be careful, is that the number is the number 1, right? Remember, so for all this kind of prime numbers, we can only add a one those numbers once, right? For example, if we already add 3 here, we cannot add another 3. But 1 is different, because let's say if we have multiple 1s here, we can add as many of them. Basically, we can freely add these 1s regardless. We can add a 1 1 or 2 1 or 3 1 or 4 1, because it doesn't really matter, because it will not affect the final product. And since the index for these ones are different, that's why we need to consider them separately. Which means this is gonna be like what? So whenever it comes to 1, it'll be like a full subset without any constraint, which is what? Which is gonna be the 2 to the power of n, where the n is equal to the count of 1, right? Because like when it comes to no constraint subsets, every time we add a numbers here, right, the total count will be doubled, right? So that's the last thing we need to be careful. Cool. So I think we can start our implementation then. Okay. First, let's do a prime, right? So because since we need to build like a bit mask for all the primes numbers, we need to find all the primes within this range, right? So how do we do that? A straightforward way is like this, right? We simply just start from 2 to 30, right? Because prime numbers start from 2, right? And for each number, we do a check, right? I is going to, so we do I equals to 2 and y. Well, the square of I is smaller than number, right? So if the number do modulo of I is equal to 0, and then it means that it's not then it means it's not prime. Okay, and then we break, right? So if the is prime is true, and then we add its primes to the prime list. Okay, because the definition of a prime number is that a prime number can only be divided by 1 and itself, right? That's why we stop when the basically we only try square root times of this number. If any of them can be divided by this I, then we mark it, then it's not prime, right? There's no need to go over that, right? Go over the square root number. Okay, cool. So now we have that. We have a prime list, right? Or you know what? Since this one is pretty small, you can just manually write down the list. It's up to you. And then we have a count, right? So the count is going to be a counter dot numbers. Okay. And then our DFS, right? DP is going to be the I and mask, right? So this means that we are processing this number, and the mask means that the mask is representing what are the how many prime numbers we have used so far. Okay. Okay, and none, right? Cool. And to start with, you know what? Let me do a keys. I'm going to get all the keys so that we can loop through from by index. Okay, and then we have n is gonna be the length of count, right? And then here we return the what? We return the dp of starting from 0, and the mask is 0 because at the beginning everything is it's not used. Okay, and we do a -1, right? We do a -1 to remove the empty subset, right? And then we have a mod 9 plus 7. Okay, but you know here okay, you know, I'll handle this last part later. Let's implement this DP because we haven't handled that one case, but we'll do that later. So let's finish this DP part. Okay, so now we have that, right? And oh, how about, so the basic is whenever I is equal to n, it means that, okay, we have reached to the end. Basically, we have traversed to everything, and then it means that, okay, we find one subset, possible subset, right? By either like picking some numbers or don't pick at all. But regardless, we have already traversed to the end of all the numbers. Okay, and then we have this number, right? So number will be what? Will be the keys of I, right? So keys of I. Okay, so first one is not pick. Okay, not pick current number, which is going to be the answer equal to the dp of I plus 1 dot mask, which means we're not doing anything. That's why the answer will be the same as the previous as the next state, right? So if we don't pick the current one, it will be whatever we have, right, of this one. Okay, else we pick the current one. Okay, pick current number, right? But to pick the current number, but to pick the current number, we need to check something, right? And then we return the answer in the end. So first we need to check, we need to have like the mask, so the prime mask, right? So the prime number is mask for the current answer, for the current number. And how can we do it, right? We can do this. So basically we try to, for current number, we try each of the prime numbers. Okay, we try to divide it, do a modular with each of the prime numbers. If any of the modular is equal to 0, then it means that, okay, so the current number will have that prime number, right? And then in the end, right, because in the end we want to like accumulate everything together, right? Because so let's say we have 2, 3, the prime is 2, 3, 5, 7, 11, 13, right? So let's say, okay, so let's say the current number is what? The current number is 35. Okay, so we need this two number to be marked as 1. Okay, and how do we do it, right? So since we already have the prime numbers here, right, we simply just need to do like, so basically we'll get for each of the numbers, whenever we know there's a prime number for this one, we're gonna do a bit shift. Okay, so when we see 5, right, we'll have what? We'll have 0, 0, 1, 0, 0, 0, right? Because the index for this prime we already know that, right? And then what? And then the how about 7? Then probably when it's 7, we're gonna have like 0, 0, 0, 1, 0, 0, right? And then we want to accumulate them together, right? Which is gonna be a XOR, or sorry, not XOR, but or we do a sum, because or in the bitwise is equivalent to the sum, right? That's why we can do a sum of this for what? For I dot p, right? The prime numbers in enumerate of primes, okay? If the num divide modular p is equal to 0, okay? So we have what? We have this kind of this one, right? That's how we get the bit mask for all the prime numbers for the current number, okay? And then we can do our check here. So first, we need to make sure the current number itself is not a bad one, right? So what are the bad ones? So for example, I already talked about that. So 4, 9, and 25, they are bad, right? And anything that's can be divided by these three numbers are also bad, right? So which means if we need to make sure if this one is not equal to 0, and the number of this 9 is not equal to 0, and number to a modular of 25 is not equal to 0, right? And the last one is this, and the last one is mask to an end of this prime mask is also equal to 0, right? Then this one means there's no intersection of the prime numbers, which means we can use the current number. And which means we can accumulate this one to the dp of I plus 1 dot mask prime mask, right? Because after choosing these numbers, we need to mark those prime numbers to be used, which means we need to mark them into 1, right? And then don't forget to do a count, right? To multiply by the count if we have multiple numbers, right? And then in the end, we return the answer. I think that's it, right? Okay, cool. But there is like a special case we haven't handled yet, which is 1, right? So all this stuff, they are for at least this part is for non-1 numbers, right? Because for non-1 numbers, that's when we need to do this mask checks, right? But whenever it is 1, right? Whenever it is 1, what does it mean? It means that okay, so for 1, actually we're assuming that we're assuming that we're not going to pick ones. We're basically we're completely ignoring 1 because we'll be do a 2 to the power of 2, and then we do a count of 1, right? And then we do a modular because this is what we'll be doing in the end to handle ones, which means we will completely ignore 1 in this main DP function here. Then how can we do it, right? So basically, here is not picking current 1. You know, we cannot do this. If number is equal to 1, we simply return here. This is wrong because we still want to continue. Basically, we want to ignore it, right? It means that here we're ignoring the current number, right? But here we're trying to pick it. So all we need to do is we simply just need to ignore it here, right? We add one more statement if the number is not equal to 1, and then we continue. If it's 1, we always skip the current one. Okay, I think that's it. Or I think there's another way that I think you can maybe sort this key, right? Basically, you can sort this key from the smallest to the biggest, and then you simply just start processing from we are just processing from, let's say we have 1, 2, 5, and 7. We can just start processing from 2, right, instead of 1. Yeah, I think that's another option. But anyway, I think if we don't sort it, you have to add one more statement here to exclude 1 in this case, in the pick the current number case. Okay, and the last thing is like this. I think, okay, so let me try to do this. So we do a like 2 to the power of n. The reason we do a like power with modular is because if 1 is pretty big, right? Let's say if the 1 is we have 10, let's say 10,000, right? They're all ones, right? Then if we do a 2 to the power of 10,000, this will be too big. That's why we in Python we have this kind of power function with a modular that can give us like a reasonable answer for this power. And then in the end, we do another modular, right? And I think that's it. Run it. Oops. Okay. Okay. Run code. Okay. Accept it. Okay. What? Did I? Let's see. I thought this should work. Let me see the prime. Are we doing? Okay. It's here. Power, right? I times I, or I should do this. I times I, right? Let's try again. Okay. Okay. Cool. So this one works, right? Yeah, I think that's it, right? I mean, as for the time complexity, we have what? So let's say this one's n, right? So we have n times the mask. The mask is like what? Is also 2 to the power of n, right? So the mask is the length of the what? Is length of the prime numbers, right? Which is, I think, which is also 2 to the power of n. Okay. Yeah, the prime number will be a little smaller than n, but I think it's still in the scale of n, right? And then here we don't have anything, right? We just either we pick or we don't pick. Okay. Yep. I think that's it for this one. And yeah, another subset problem, another constrained subset problem, right? And in this case, the constraint is from the prime numbers, right? Basically, the each subset can only have distinct prime numbers, right? And then in order to do that, we create a bit mask, right? For the prime numbers, we have already been used, and then for each of the number, we create like another bit mask for the prime number that will coming from the new number, right? And then we check if this two doesn't have any intersect, and then we use this number, okay? And then we also want to make sure the current number itself is a good number to use. And lastly, is this kind of count thing, right? We have to make sure we need to know instead of traversing everything, we can just do a count in the end. And then the last thing is this one thing, right? So yeah, a lot, many minor traps there, right? But there you go. That's it. Okay. And thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.